not with you guys, unfortunately. Um, I'm in Colorado, somewhere in the mountains. I'm attending a different conference, but it's always my pleasure to be part of the short course. And yeah, so today we're going to talk about microscopy in cells and tissues. It's laser scanning based microscopy, and I will emphasize nonlinear optical contrast mechanisms that you can use to learn a whole bunch about your sample. Okay, so let's dive in. Okay, come on. Yo, it doesn't work. Okay, so what is the general idea? It's very simple. We have our biological material. It could be anything, but let's say a piece of tissue, in vivo, ex vivo, it doesn't really matter at this point. And we'd like to know what's in it. What is the morphology, but also maybe, where are our favorite bio components? For instance, a tissue component that you're interested in. Can I see it? Where is it? How does it behave? Is it chemically altered? Is it in a disease state, or is it healthy? And so we'd like to do that with light. Light, of course, is a great tool. In the most ideal situation, what you'd like to do is send the light in and get the light out, and the light that comes out tells you a story about what's going on inside. Okay, and ideally, you don't perturb the tissue or cells that you're investigating. So it becomes a non-invasive or completely non-perturbative kind of probing approach. And it's extremely powerful, and I guess this is why you guys, are here at this course. So there's a whole bunch of ways to do that. The simplest way is, look for a contrast mechanism that is offered by sending light onto your material that is, the least, I would say, affected. Okay, so that it affects the tissue in the least possible way. So here's one example that is the so-called phase delay, and everybody's familiar with it. You have here, for instance, a piece of glass, light goes through it, so that means nothing gets absorbed, okay? Nothing gets absorbed, but you can still see it. I can see that there's some material sitting there, and the reason why you see that is because there's a lot of refractive effects, okay? So, and phase delay is one of them. So if you send your light just head on through this material, then you can still notice that it passed through this material, even though there's no absorption, because its phase has changed, okay, as it propagates through it. And that's because basically this material, of course, is composed of a lot of atoms and electrons, and those electrons in particular respond to the light. They start to oscillate, and that oscillation has an effect on how the light can propagate through this material. So the light is affecting those electronic motions inside, but those electronic motions also affect the light that propagates through. So it's basically this light matter interaction that is responsible for this effect. Now, the phase delay is actually extremely powerful, and I must say that phase delays have seen a new renewed interest within the community because it's so simple to do, and there's actually a lot to learn. So this is a DIC image, differential interference contrast image of a cell, and you can see there's a tremendous amount of detail that you can learn from, right? Mostly morphological. And so in many cases, this kind of contrast is enough to say something about the state of your cell, what the cell looks like, if it's different, if it has a response to some kind of stimulus. And so this is a simple but yet an extremely powerful approach to learn about your sample. What it does not do, of course, is to tell you what molecules are in there and where they are. Okay, and that's because all molecules contribute to this effect. It's a general effect and not really molecular specific. And so that's where it stops. And if you want to learn more about where is my favorite target, my molecular target, then you have to do something else. And then you have to use a different kind of optical contrast. And so the simplest optical contrast you can think of possibly is simply absorption. Okay, so here's a molecule. This is a rhodamine 6G molecule, a well-known molecular dye. It absorbs really well. But on this slide, I'd like to emphasize a little bit, what does it mean, absorb well? I mean, how strong is that absorption really, and can we leverage it to do imaging with? So it turns out that the efficiency of absorption can be quite nicely summarized with this sigma. That's the cross-section. That's the molecular absorption cross-section. And there's a number there. This is the number for rhodamine, 10 to the minus 16 centimeters square. That means it's an area. And so the unit of cross-section is indeed area. Now, what does that mean? That means that, first of all, it's a very small number. And the area means that the molecule looks to be of a certain size to the incoming photon. And the smaller this molecule is, the less the photon can interact with this molecule. Okay? So this number here, which is tiny, indicates that the interaction perhaps may not be that strong. Now, here's a little exercise that I always like to do with people. I have here, this is a Gedanken experiment. Okay, so I have here a cube of 1 centimeter. Okay, and then I come in with one photon. This little line here is just a flat wavefront. Okay, that's a plane wave. It's one photon. It's going to be incident on this 1 centimeter cube. And inside this cube, I'm going to put in these rhodamine molecules. And my question to you is very simple. How many of these molecules do we have to put into this little tiny cube to be sure that this single photon will be absorbed? Okay. Think about it for maybe a couple of seconds. If you know the answer, just like, let me know. Anybody? All right. Well, the answer is actually 10 to the 16. Okay. You have to put 10 to the 16 molecules in there in this cube to be sure that that single photon is absorbed. Okay. So it's kind of interesting, right? Because that is a lot, and that indicates that the absorption interaction perhaps is really not that strong. Now, another way to look at this is the following. If I look at sigma again, and I write it not in terms of centimeter square, but nanometer square, then I can say, oh, the actual area is 0.1 times 0.1 nanometer square, or an angstrom square. Okay? An angstrom square is pretty small. It's actually smaller than the molecule itself. Okay? That is the optical size of the molecule versus its physical size. Now, if you are able, this is just another interesting aspect, if you're able to take the photon, the freely propagating photon, and you be able to compress it on a very tiny little scale. In fact, the scale about an angstrom squared. If you can do that, okay, if you can compress it in size to that level, then in fact, the interaction is 1-to-1, and you use only one molecule to absorb that single photon. Okay, so there's an interesting thing here. And people, if you're interested in molecular sensing, and you may have heard about plasmonics, surface plasmons, they do something like this. They compress the light to a very small scale, and at that scale, the interaction is much, much more efficient. And this is just one way to think about it. This is another example that I really like. That's retinol. Retinol is the chromophore in your eye. You probably know that. But we just talk about how inefficient absorption really is. And also, if you compress this plane wave of the single photon to a smaller size, if you're able to focus it perhaps to a smaller spot, then the interaction, in fact, is more efficient. Okay, and so that's why the eye actually has a lens, and the numerical aperture of this lens, the NA, has a certain number. It turns out to be about 0.23. Okay, so the numerical aperture of your eye lens is about 0.2, and if you calculate what kind of focal spot that makes on your retina, that's about between 1 and 5 micrometers square. That is a lot smaller than the centimeter square photon that I just talked about in the beginning. And in fact, by compressing it in space, you can actually increase the efficiency of this process. And instead of using 10 to the 16 rhodamine molecules, your eye has 100 million photoreceptors. So that is a lot less than 10 to the 16. And key actually is the fact that you make things smaller. Okay, so interesting aspect, I think. Now, in microscopy, we just talked about absorption, but absorption microscopy really is not really a thing. Okay, nobody is doing absorption spectroscopy as a contrast mechanism in the optical microscope. And in fact, most contrast mechanisms are just based on emission or fluorescence. Okay, so all these beautiful images that you see are usually all fluorescence based. So it's an interesting question, like why is fluorescence so popular and absorption microscopy is not? Okay, maybe you know that, but it's really important to realize that fluorescence is indeed the preferred mechanism to see things. It's quite obvious why that is, because in absorption, what you do, you look for a very tiny little change in intensity of the light that you send through your sample. So if you send 1 million photons in to get absorbed, then you're looking for a very small change on a huge background. Very hard to detect. In fluorescence, it's the other way around. Even though absorption is not so efficient, okay, perhaps, if it gets absorbed, so if a molecule absorbs a photon, then it re-emits it at a different color, which is extremely easy to see. So in fluorescence, you only see the successful events. You don't see the events that were unsuccessful. And that's a problem in absorption. You see a lot of unsuccessful events that give you no contrast. Okay, so fluorescence definitely, from an optical point of view, is a much better way to examine your sample. So, lots of microscopes look like this. You have a beautiful microscope frame. You have a computer here, and it's a useful tool, and I'm sure you have worked with one of these systems. Now, in fluorescence microscopy, which is really the gold standard, there are some issues, okay, that we're going to talk about and try to do something about. So, in tissues and in some let's say spheroid samples, putting molecules in that absorb and fluoresce is actually kind of difficult. Okay, so not all structures are easy to stain with fluorophores. Another thing is that the visible wavelengths at which these fluorophores absorb is not so great for examining tissues because visible wavelengths scatter a lot, and so you can go really deep. That is definitely a problem. And one way to go about it is to think about nonlinear interactions. Now, this is kind of strange because I just told you maybe 5 minutes ago that linear absorption is actually fairly inefficient. And now I'm going to talk about nonlinear interactions. So we go from linear to nonlinear, and supposedly that doesn't make things a lot stronger. And that is true. Nonlinear typically is a lot weaker than linear. Okay, so what is the reasoning behind this? Why would we make things more complicated? The reason behind it is that it turns out that even though it's weaker, there are situations where it can be still pretty strong, and the contrast that you get is actually kind of unique. It can be extremely beneficial for your experiments. So here's a kind of a very simple cartoon of what nonlinear interactions really do in your material. Here's a photon. This is a photon, okay? It has a frequency omega-1. So it's hitting my sample, and my sample I simply represent as maybe some molecule that starts to oscillate. Okay, so let's think about this membrane here as like an electron cloud that is, wobbles back and forth at the same frequency with which you send in the photon. Okay, so this is 800 nanometers. Then this wiggling is basically the frequency of an 800 nanometer photon. All right, so then the wiggling basically stops. In fact, it re-emits a photon, and this is what you get out. Okay, so simply one photon in, one photon out. Now, it turns out if you are increasing the amount of photons that you put in up to a certain point, you are starting to drive the system so hard that the system goes like in a kind of in a nonlinear regime. So you think about this in the following way. At least I like this analogy a lot. If you think about your membrane in your ear, if you drive it really hard, okay, so if you smack a tone really hard on the piano, then you hear like a very high tone at the same time. That's an overtone. Okay, that overtone is an indication that your membrane is not oscillating at the original tone, but actually oscillates at higher frequencies as well. Okay, and that is a nonlinear response. So that's something like this. If I drive really hard, then this membrane actually starts to pick up oscillations that are overtones of the original. Okay, and so what you get out, in fact, you do get out the color of the overtones. And in terms of optics, in terms of photons, that would mean a photon of one frequency in and a photon of double the frequency out. Okay, so molecules like membranes in your ear, they can do that. And as soon as they hit the nonlinear regime, they can produce colors that you didn't put in. Okay, so this response is a nonlinear response, and we're going to make use of that. Okay, so this is kind of the photonic picture. 2 photons in, let's say. I drive it really hard, and I get 1 photon out of double the frequency. Energy is conserved. Omega plus omega equals 2 omega. I put 2 in, I get 1 out. Okay, but that photon now has a different color. So this is the Jablonski diagram that people typically draw. And so that means the following: one photon in, another photon. Okay, so two photons. They combine their forces to drive the system. The system responds by producing a photon of double the frequency. So this is second harmonic generation. This is another flavor of it. I can just put in two different colors and then drive it in such a way that I get a combination frequency out. Okay, so it's some frequency. And below, I can do it in the following way. I have two different colors of photons. They can combine omega 1 plus omega 2. And the Jablonski diagram would look like this, for instance. One photon of one color, another photon. Combination of the two produces a photon of a different color. So that will be some frequency generation. Okay, now what does that mean for my molecule? How can I think about this? Well, let's think about this rhodamine molecule again. I'm going to drive my photons this electron cloud here. Okay, so I'm going to drive it like that. It's going to wiggle. Okay, it becomes polarized. The molecule becomes polarized. And if I do it kind of like mildly, gently in the linear regime, what I see is that I drive that system in a kind of a very nice harmonic fashion. Okay, so this diagram here, this graph, indicates that if I come in with my electric field of my photon, then I push the electrons to one side, and then a moment later it's pushed to the other side. So the distance of the electron cloud is changing. But it can't change too much because this is a potential here. So the more you push it out, the more you see this potential barrier, so it pushes it back. Okay, so there's a limit to how far you can push these electrons. Now, if I start pushing it harder, but that means that I'm getting farther out. That means I'm getting higher and higher up this potential energy curve. Okay, so if I drive it really hard, then what happens is that I'm going to move away from the linear regime. So if I'm here at the bottom of the well, I'm driving it kind of gently, then the response is linear. That means the polarization that results is directly proportional to the strength of the electric field. And the proportionality constant, or more like a tensor, is this thing here, which is the susceptibility. Okay, that's the linear susceptibility of the molecule, of the material. If I drive it harder, that means I move farther out. That means I'm going to sample higher parts of this potential energy curve. And up here, it actually starts to deviate from a purely harmonic potential. Okay, that means it's no longer a harmonic potential, it's anharmonic. And as soon as it's anharmonic, you start sampling those parts, that means you're going to pick up overtones or nonlinearities. And therefore, you get components such as a second order component in your polarization, which scales quadratically with the incoming fields. Okay? And the proportionality tensor is now chi2. That's the second order susceptibility. If you drive it even harder, you can pick up third order effects. So the sample response with this tensor, which is the third order nonlinear susceptibility. You see three fields now are involved to produce those oscillations that are third order in the incoming fields. Okay? So that's how we indicate the nonlinearities. Typically, we think about them in terms of these susceptibilities. So from linear to nonlinear, and there's a whole bunch of nonlinearities.
Eric, could you comment, going back to your previous slide, can you comment on what gives rise to the asymmetry of that potential well? Because you have the asymmetry, because you have that deviation only on one side as opposed to both sides. Could you just give some insight about that?
Yeah, okay, that's a great question. So, I drew here a potential where you can see that on one side, if I drive the electrons on one side, there it's easier to pull them out than on the other side. On this side, it's steeper, so it's harder to pull them out. It's an asymmetric potential. Okay. I can also think of a potential that is actually symmetric. It's anharmonic, so it curves like, for instance, this way. But on the other side, it's the same, and it also curves like that. So the shape is basically the mirror image on this side, on this end. There will be a symmetric anharmonic potential. Now, both potentials are nonlinear in the sense that they produce optical nonlinearities. Some nonlinearities are evident only in this kind of shape, and other nonlinearities are valid for both. Now, it turns out that this second order one needs to have a potential that looks like that. Okay, that needs to be asymmetric, and that is somewhat important in some cases. Okay, so does that make sense? All right.
There's another question in the audience.
Yeah.
Please.
Is the electric field that's in the equations, is that the incident electric field?
Yes.
Okay.
Those are electric fields that come in to your sample. And right now I just make this like one E, but these two E's here with the square, actually it could be E1 and E2. Okay, so that could be of different frequencies, in fact. But here I just write them as being the same.
I guess the question I had is kind of, is there a general characteristic on a simplistic level that you can explain what type of molecules have an asymmetric potential versus ones that have symmetric nonlinear potentials?
Yeah. That's in fact, I mean, if you look at this guy here, the rhodamine molecule, if I look on this side of the molecule and that side of the molecule, it's very similar. So if I shake this electron cloud in this direction, then in fact it will be an asymmetric potential. Asymmetric potential that is still, symmetric potential that is still anharmonic. So it can be anharmonic, but it's symmetric. Right? So actually a lot of molecules don't have that necessarily. They have some sort of difference, and that leads immediately to a potential that is asymmetric. Yeah. In fact, most molecules have an asymmetric potential. In fact, most molecules have a non-vanishing second order nonlinearity. Okay. Only purely symmetric molecules don't have that effect. But in biology, almost all molecules have some sort of a second order nonlinearity, as we will talk about in a few moments. Okay, so how strong does that field have to be for you to see those effects? And one way to think about it is the following. This field, EA, is the atomic electric field that holds the electron close to the nucleus. Okay, so that is a binding field that binds the electron to the atom. If you start driving really hard, so if you come in with a field of this magnitude, what will happen is that you kind of compensate for that, and therefore you kick the electron out. Okay, so if you do that, then the electron becomes extremely loose, and that means that you sample very high parts of the potential. So this is a good starting point to think about how strong do these fields have to be. If you take that number and you convert it into energies or intensities, then you get 10 to the 14 watts per centimeter square. Now that may not tell you a lot, but if you compare that to the intensity of sunlight on Earth, which is 0.13 watts per centimeter square, you see the difference. Okay, so this indicates that if you want to see strong nonlinearities, you have to come in with a lot of light. Okay, sunlight certainly cannot do it. This is the electric field, which is way smaller than the electric field here that keeps the electron bound to the atom. Now, what do we do then to see it? And in fact, you couldn't see it until the 1960s when this thing came along. This is the laser, of course, and it can produce electric field strengths of your photons that are actually pretty high. Okay, so 3 times 10 to the 6 volt per meter is actually easily achieved. But that is way stronger than the electric field produced by the incoming sunlight. Right now, you can see it's not quite 10 to the 10. This is 10 to the 10, 10 to the 6. So it seems like we're still missing a couple of orders. So you may know that the laser was invented in 1960. When did people see the first nonlinear optical effects? It turns out the next year already, and that was second harmonic generation. 1 year later, third harmonic generation was published. And here's another interesting one. This is the same laser that you saw on the previous slide. This is the ruby laser. And back in the day, people put this thing in there. This is the Kerr shutter. It's one way for them to produce very strong pulses. This Kerr shutter is a way to kind of make the cavity suddenly transparent and then kick a lot of energy out. Okay, but for us, what is interesting is that a Kerr shutter was simply a cell with this molecule in here, nitrobenzene, and the laser had a wavelength of 694. Okay, 694 nanometers. But it turns out as soon as you put a Kerr shutter in there with the nitrobenzene, then a small little peak comes out as well. Right, and that peak was shifted by a total of this energy, which is indicated in reciprocal centimeters, 1344, and that turns out to be the Raman line of nitrobenzene. Okay, so this was the first demonstration of a technique called stimulated Raman scattering, also in 1962. So within 3 years of inventing the laser, all basic nonlinearities that we will be talking about were all demonstrated, okay, in the early 60s. Kind of amazing if you think about it. Now, for us, it turns out that those nonlinearities, even though they were demonstrated very early on, did not really have an impact in microscopy, okay? And that only changed in the 1990s. This paper is seminal. It's called Two-Photon Laser Scanning Fluorescence Microscopy by Watt Webb's group from Cornell University. And this paper really set up the field of nonlinear optical microscopy, okay? And the technique that they used was basically two-photon absorption followed by fluorescence. So two-photon excited fluorescence was the first demonstration of biological imaging with nonlinear optics. So since then, a lot of things have happened. And so we have a whole plethora of nonlinear optical contrast mechanisms that we can take advantage of. Second harmonic generation, we have seen already. It's a popular technique to see collagen, and I'll talk about that. Third harmonic generation, so 3 photons in, 1 photon out, is a popular technique to see small morphological features in cells and tissues. Some frequency generation, very closely related to second harmonic generation. So you can see the same things, collagen, but now you can see a little bit of chemical contrast as well, or 2-photon excited fluorescence. Again, 2 photons in, and then a small relaxation, then a photon emitted through fluorescence. Extremely popular technique, and you can use it in a so-called non-label kind of way, so label-free way, because of the presence of some molecules that are naturally fluorescents, for instance, NADH, FAD, elastin, and even melanin, turns out. So that gives you some beautiful molecular contrast of tissue samples. So what I'm going to do now for the remainder of this presentation, I'm going to talk about 3 techniques that are very well known. 2-photon excited and 3-photon excited fluorescence, harmonic generation, and also probing vibrational motions through a nonlinear Raman effect in the microscope. Okay, so I'm going to talk about a little bit about why these techniques work and what they really probe, and then what you can do with them.
Eric, let me just pause because you're kind of changing the theme here. So
Yeah.
just to see if there are any questions in the audience before we do that. Any questions on fundamentals of nonlinear? Yes.
So the nonlinear light types, the previous slide with the SHG, THG, SFG, like those 4 different types, are those the 4 types that we talked about in where we're doing P1, P2, P3?
Yeah, so I will highlight some of that in the following. So these 3 examples that I showed to you, I will tell you what order they are, and so which nonlinear susceptibility is responsible for the response, and also how that relates to really the molecular response. So what does the molecule do to produce a signal like that?
Other questions? Okay.
All right. Okay, so here, this molecule here, you may recognize, this is NADH, okay? NADH, and so NADH is an interesting molecule, there's an interesting structure, but for us, it turns out that this part of the molecule is the part that responds to our incoming light, okay? That is the so-called chromophore part of the NADH molecule. So if we want to excite it, what we have to do is we have to come in with a photon that can set into resonance this part of the molecule, okay? And what we do then, we excite the molecule to an excited state, right? And then we hopefully can observe some fluorescence. Now, like I said, the sigma, which is the cross section, is an indication of how well the molecule can absorb a photon. And in this case, it's just 1 photon. Cross sections, typically in the literature, you see them written simply as sigma with a number, but it turns out you can actually relate that to what's happening in the molecule. And the key feature is really how strong do you polarize this part of the molecule. So another way to think about it, if you move this thing back and forth, you create an oscillating dipole that's actually a transition dipole. And that is this thing right here. Mu12 is simply the transition dipole that you kind of create. And so the sigma is just proportional to the square of that with a bunch of natural constants. Okay, so you can actually calculate what it is, right? It turns out if you do a measurement, then you can measure how much that is. And for a typical chromophore, it is about 10 to the minus 16 or 10 to the minus 17. So for NADH, it's actually 10 to the minus 17 centimeters squared. We already have seen the unit of the cross-section. So if you know this number, and all these numbers are known, all these constants are known, I can actually calculate how strong that transition dipole is. And it turns out it's of this order, okay? About 10 to the minus 29 coulomb times meter. Very tiny number, of course, because it's a very small effect. Okay, it's a very small molecule, and this effect is actually small as well. Now, what happens, of course, is that this excitation will relax, the energy will tumble to the bottom of this potential well, and then it wants to go back. And one way in which it can go back is under the emission of a photon. That is the fluorescence event. Okay, this guy here, this green arrow. And we can actually calculate the efficiency of this. And that is proportional, again, to a transition dipole, which is about the same magnitude as the absorption dipole. Okay? So instead of mu 1, 2, it's mu 2, 1. And the magnitude is about the same. So the higher this transition dipole is, the easier it is for the molecule to fall back to the ground state under the emission of a photon. Okay? And so you can actually deduce from that the more efficient this transition dipole is, the quicker it can fall back to the ground state. So it doesn't stay a long time here. So the lifetime will be short if this is very strong. So that is shown over here. Okay, so you see that this is the mu 2,1. That's a transition dipole. If it's very strong, that means it doesn't spend a lot of time here. And if you fill out these numbers, actually, again, this number you can just deduce. You fill out these constants, you actually get a number out, about 5 nanoseconds, okay? So for a typical chromophore, we expect a lifetime of about 5 nanoseconds. Not because, I made it up, but because you can actually calculate based on very simple first principles. So let's have a look what NADH does. NADH, our molecule that we use as an example here, 0.27 nanoseconds, okay? That is not the same as 5. So what does that mean? That means actually, this molecule falls back much quicker than I would expect based on the emission of light. And that's because there is another channel that leaks the energy back to the ground state. That is a non-radiative channel, okay? And that channel is much more efficient, and therefore it leaks out so quick from the non-radiative channel that the radiation is not really playing a very important role. Therefore, you don't get a lot of photons out, and the lifetime gets shorter. Let's look at another molecule of interest, green fluorescence protein. Okay.
So Eric, just to go back, so you said that there's another channel for the energy to be dissipated. Is that simply heat, meaning that the energy gets dissipated through vibrational modes, or?
Yes. The energy gets dissipated mostly through interactions with neighboring molecules.
Got it.
So neighboring molecules bump into the molecule and they kind of extract energy from the molecule.
So it's not like the lifetime from a radiative standpoint, the lifetime is 5 nanoseconds. It's just that after about 1 nanosecond, there's no energy left to go down through the fluorescence.
Correct. Okay. So the radiative lifetime of a typical chromophore is about 5 nanoseconds. There's some variation between 1 and 10. Okay, those are typical numbers based on a transition dipole, which are very similar for chromophores. Mm-hmm. So if you see a lifetime that is much shorter than a nanosecond, that means that there's a very strong non-radiative channel. Okay, and that means that molecules in the surrounding bump into this chromophore all the time and they extract energy from it.
Got it.
Now, this GFP 2.7, which is only half of this, which means this is a very good fluorophore, okay, because this guy doesn't lose it through non-radiative channels. And GFP, of course, is in a barrel, in a protein barrel. This chromophore is hidden in this barrel. It's protected, and that is one of the reasons why the lifetime is longer and the efficiency, the quantum yield, is higher. Okay, so that was just one photon. Remember, so who's the first person to propose to use 2 photons or even 3 photons? And that turns out to be, believe it or not, our good friend Albert Einstein. Okay, so in 2005, a very important year for him. He basically suggested that you could actually use multiple quanta of light to deliver that to a molecule, for instance, in one step. So that was just a suggestion. Nothing was done with it, in fact, until Rupert Meyer actually said more or less the same thing, but actually calculated the whole thing out. Okay, beautiful paper, very detailed. This is the German title, as you can see, which means about or on the probability of the cooperation of two light quanta in one step. So that was 1929. Now, 1929, the laser didn't exist. So she predicted almost everything that there was to know about this process, but nobody could actually prove it because lasers didn't exist yet. Okay, so how does it change? How does the picture change? So let's come in now with a photon that is half the energy. I'm still starting to polarize this part of the molecule, but the polarization is not enough to actually click into the excited state. So, but if I have another photon to help me out, so two photons at the same time, I can make that transition and then basically end up in the same kind of situation in the excited state. I can tumble back and then emit. So, what is the efficiency of this? How do I describe that? Well, the cross section for the two photon absorption process is now the following. Again, a bunch of constants here, right? And then, lo and behold, that's our nonlinear susceptibility that I just introduced about 15 minutes ago, chi3. Okay, it turns out that two photon absorption actually, from a light matter interaction, is a third order interaction, believe it or not. Okay, and so this thing, the imaginary part of this tensor here, is responsible for the two photon absorption process. Okay, now we can measure these things, and we can therefore measure the sigmas. And if you look at that, the sigma, two photon absorption sigma, for NADH is the following: 0.035 times 10 to the minus 50 centimeter times second per photon. Okay, couple of things. This unit is a terrible unit, and therefore people say, let's call that whole thing 10 to the minus 50 with these constants or these quantities behind it. Let's call that Rupert Meyer. Okay, after Maria Rupert Meyer. So therefore, this sigma for this molecule here, NADH, the two photon absorption cross section is 0.035 Rupert Meyers. What about GFP? GFP, 39 Rupert Meyers. So that means that GFP, once again, is a much better chromophore and a much better fluorophore. It absorbs in one photon and in two photon much better than NADH does. Okay, so this is another fluorescent protein. This is red fluorescent protein. This is the absorption spectrum of red fluorescent protein. This is the one photon excitation wavelength. You can see here. Okay, so it peaks at 550. What does the two photon excitation spectrum look like of this fluorescent protein? You have to look at the bottom axis now. So that means that all these numbers are multiplied by 2. So let's do that and then see what it looks like. It looks like this. Okay. Now, the first thing you should notice that there are some similarities and there are some differences. Similarities, I see here the same two kind of bumps, the bump here and the bump there. They kind of overlap more or less, although the ratio is different. But then here on the higher energy side, I see actually features that I don't see at all in the one photon absorption spectrum. Okay, and the reason for that is the following. This first part here, I'm exciting from the ground state to the first excited state, either in one step or in 2 steps. Okay, but the overall effect is more or less the same. Okay, so I see the same kind of features. But here, something else is happening. So here, I'm exciting. This little bump here is actually from the ground state to the second excited state potential, right? So higher up. And I can also do it in 2 steps, as you can see. But this photon here, this arrow, gets pretty close to the resonance of S1, and therefore it gets enhanced. This is basically electronically enhanced 2 photon absorption. And you see that immediately a huge feature shows up because of the implied resonance of 1 photon within the 2 photon process. Okay, so the message is the 1 photon and the 2 photon absorption cross spectra are not the same. They can be quite different, in fact.
So Eric, does that mean, sorry, interrupt. Does that mean that if you actually do multi-photon at a wavelength equivalent to the 1 photon primary peak, you have because I just see that that red is continuing to increase at 700. If you go towards 550, you get just a huge 2-photon peak because basically the first photon already populates this first singlet state.
Yeah. I mean, I would say this is more like a resonance enhancement effect. Okay, so it's not that you populate this; it is resonance enhanced. So that's why it peaks over here. But yeah, if you excite here in this range, so if you excite at 750, you get a very strong absorption effect, 2-photon absorption effect in this red fluorescent protein that you wouldn't expect based on the single photon absorption spectrum.
Right. Okay, another question. There's another question.
About the sigmas. So the 2-photon sigma have different units than the original sigma you showed. Is there are those two different kinds of sigmas?
Yes, I mean they are both sigmas.
Yes.
But you can imagine that the 2-photon absorption cross section must have different units.
Yeah.
Because it actually scales differently with the incoming fields. So if you I can write it differently. Like sigma times the field needs to be something that's proportional to intensity. Okay, the detected intensity. And if you have, instead of having one field, I have 2 fields coming in or 4 fields coming in. That means that the unit of the sigma must change.
Okay.
So yeah, they must have different units, in fact.
Okay. Thank you.
But they have the same physical meaning. Okay, they mean the same thing. They mean they are both a measure of the efficiency of the absorption event, either 1 photon or 2 photons. All right. So
Go ahead.
Okay. So like I said, this 2-photon absorption process is a Chi-3 effect, maybe counterintuitive, but true. And it's a long story to explain to you why that is. I don't have time to do it, but you can approach me maybe later on, and I'll try to explain it to you. So the bottom line is that it works, and this is a beautiful 2-photon excited fluorescence image of elastin in tissue, but there's a whole bunch of things that actually fluoresce and are very good at responding to a 2-photon absorption process. So this list of molecules are popular targets in 2-photon excited fluorescence microscopy, and they produce reasonable signals. Okay. You also see here 3PE, that is 3-photon excited, and 2PE. So both 3-photon and 2-photon excited processes can give rise to fluorescent signals of naturally occurring chromophores. So let's look at what does it mean from an optical point of view. So here's my my point spread function. Okay, so this is basically the point spread function in 1-photon absorption, which is basically the airy disk. Okay, this is XY. This is the lateral extent of my focus, right? This is the XY, the XZ extent, so the depth of my focus that I use to excite my fluorescence if I do 1-photon excitation. If I do a 2-photon excitation, then I see the following. So I have a chromophore that I want to excite, either with 1 photon or 2 photons. Let's say the chromophore absorbs at 400 nanometers, okay? If I want to excite it with 2-photon excitation, I have to use double the wavelength, so 800 nanometers. So if you look at the excitation volume of your focus, actually the focus grows a little bit bigger. Why is that? Because you use twice the wavelength, okay? Now, you have twice the wavelength, so the focus is larger, but you also have to square it because it's twice the interaction. So it's 2 effects. You have a broadening effect and you have a thinning effect because of the squaring, but the broadening effect, this wavelength effect, actually wins. And you can see that the excitation volume in 2-photon excitation, in fact, is larger than for 1-photon excitation, exciting the same chromophore. If I use 3-photon excitation, it's the same story. But for 3-photon excitation, the excitation volume swells because predominantly of the longer excitation wavelength that you use. Okay, so if this is 400 nanometer excitation, this will be 1200 nanometer to do the 3-photon excitation. Okay, so that's maybe counterintuitive because you think, oh, if I go to higher orders, I'm gonna have smaller focal volumes. That's not necessarily true. But let me show you the following, because this is a better way to think about it. So here I have my 1-photon excitation volume, and I'm going to have a layer of fluorescence molecules that I'm going to scan through focus. Okay, so I'm going to scan that layer through focus and collect the fluorescence as a function of the position of this fluorescent layer. If you do that, you see this. Okay, so this is basically the depth. Okay, so I'm scanning the layer through this thing according to this axial scan. This is the axial axis. And you see, there is no difference. Okay? How can that be? I can clearly see it's more intensity here than there. And that's because if you integrate over the entire plane, it's the same. Because the number of photons that come in any plane is the same. Okay? I send 100 photons in, they come through a plane, and then they focus, still 100 photons. And then they deviate once again, but still 100 photons. So if I have a fluorescent layer that is uniformly fluorescent, the signal doesn't change. Okay? Now, if I do the same thing for 2 photon, I see this. So for 2 photon, clearly it makes a difference because here the excitation density is the highest, and because it depends non-linearly on the incoming fields, it actually peaks around 0 because there the concentration of light is the highest, and the square is way higher than the square below it. All right, so you see here that 2 photon excitation has actually intrinsic depth sectioning that the 1 photon doesn't have. Now, if you do 3 photon excitation, you get the following. You see a slight broadening. That is what we expect based on the wavelength argument. So you seem to be worse off. But there's a very important difference, because if you go to the tails, you see that this 3 photon excitation falls off way quicker than the 2 photon. And that is extremely important, because this is the so-called out of focus signal generation efficiency, which is much lower for a 3 photon than for 2 photon. So that means, to make a long story short, that 2 photon excitation you can use for sectioning, but the out of focus light is higher than for 3 photons. Okay? So if you do the following, if you look at the 3 photon absorption followed by emission, that turns out to be actually a chi-5 effect. Okay? Kind of a higher order effect from a light matter point of view, light matter interaction point of view. But the beautiful thing is that you can go pretty deep with this. Okay? And Chris Hsu from Cornell is really the champion of this, and he's done some amazing work. And this is basically a section. This is a labeled vasculature in the brain, and you can see you can go pretty deep, beyond a millimeter, which was previously thought to be really hard, if not impossible. You can do it with 3 photon excitation. This plot is a calculated plot based on tissue properties, okay? But it actually tells you a whole bunch of things. So if you look at the y-axis, which is the amount of fluorescence that you expect from a scan like this, as a function of depth, in 1 photon, at the beginning, the 1 photon excitation is way more efficient than 2 photon or 3 photon. Okay, so but if you go down, if you go deeper, the scattering of that of the 1 photon wavelength is so high that you can't really make a compact focus anymore, and therefore you lose your efficiency pretty rapidly. That's the blue line. For 2 photon, you start lower, but at some point, about 300 microns deep or so, actually the 2 photon is more efficient than the 1 photon. And then the 3 photon is way lower in efficiency in the beginning, but it takes over much deeper, about 1 millimeter in or so. It takes over, and it becomes the most efficient signal generation process. Okay, and that's all because of scattering is reduced at the longer wavelengths, and 3 photon excitation uses the longest wavelength, and it has the least out of focus contributions. Okay, this is actually a measurement by Chris Hsu, and this is in the brain. It's you see the cortex here, the white matter. You go even deeper beyond it, and what you can see is that for 2 photon, this is again labeled vasculature, it's fluorescein. This is the purple, that is the 2 photon, and in cyan, you see the 3 photon. You see the 3 photon has a much higher fluorescence to background signal than the 2 photon, so you can go much deeper with this method. So 3 photon excitation actually is the preferred way to go deep in tissues. All right, so I'm going to jump to harmonic generation now. All right, so what's up with this? So let's see what actually this signal comes from. Okay, when I was a student, I always wondered, like, where does the signal come from? So here's our potential again, and let's say I have a molecule that is really oddly shaped like this. Okay, and I start to wiggle the electrons in this molecule. Now, in this side, I can say, well, it's more difficult to wiggle it here than wiggle it on this side. Okay, so there's an asymmetry in here that is indicated by this asymmetric potential. So if I now visualize that in terms of shaking the electrons in this strange looking molecule, then the incoming field is just a sinusoidal waveform. Then the polarization that I generate is also a sinusoid, but it is slightly modified. Why? Because I said on this side, it's easier to pull the electrons out than on this side. It's harder to pull the electrons out. And that means on one side, here on this side, it's harder to pull them out, and therefore it's truncated. But on the other side of the waveform, here, it's easier to pull them out. So I get this sinusoid that almost looks the same, but it has a slight modification. On one end, it's pulled out. On the other hand, it's held back. On the other side, it's held back. So this black line is the polarization you create. And if you take a Fourier transform of the resulting waveform, you see the following. It still oscillates predominantly at omega, but there is a 2 omega component right there. You see that? It's tiny, but it's not zero, and that is going to be my signal. Right? So you basically introduce nonlinear oscillations because of the anharmonicity of how the electrons can shake in the molecule. Now, here's my molecule once again. Okay, as you can see, I'm going to wiggle it, and I'm going to now produce a 2 omega wave that comes out. That's my signal. Okay, so this molecule, this is the potential well again. As you can see, I've determined now I can generate second harmonic generation from this single molecule. But now I'm going to put one of his neighbors next to it, same guy, but now opposite direction. I'm going to turn it around by 180. And if you do that, I also turn around this potential. Now on this side, it's easier to pull it out and harder on that side. And therefore, this waveform also makes a 180 flip. And if I now detect these two waves on my detector, let's say my detector is this dotted line here, you see that these waves are out of phase. In other words, I don't see anything because they destructively interfere. All right? So this is important. That means even though these two molecules are individually able to generate a second harmonic generation signal, which is true for almost any biomolecule, if they are organized in such a way that they compensate one another in space, nothing comes out. And it turns out that is unfortunately true for almost all biological structures. So in general, in biology, we don't see a lot of second harmonic generation unless the molecular oscillators, the harmonophores, are organized in a kind of an ordered way. They all point in the same direction. Then you can see it. Okay, so it turns out that some structures in biology do that, and collagen is one of them. So let's see what is now really oscillating in collagen. So this is my diagram, 2 photons up, 1 photon down. These dotted lines here simply means that there's no state. There's no molecular state here that I can basically dump energy into. The closest energetic state is this one over here. And if you look at the absorption spectrum, that state is actually an absorption in the amide part of the molecule. Okay, so this is the so-called pi to pi star transition in residues of the polypeptide. So it is actually very blue, so that means the wavelengths are short. You see this is absorption. This is the absorption of the protein itself. You see also some aromatic amino acids that absorb a little higher. But the bottom line is, if I excite at 800, at 400, the oscillation happens. 400 is way off this axis. So I am not really close to this natural resonance of the protein. That means I'm off resonant. The closest oscillator in my molecule or in my collagen is actually these oscillators, which is the amino acid oscillators. Okay? So I'm driving them very vaguely, very weakly. So all SHG microscopy is performed under so-called non-resonant, electronically non-resonant conditions. All right, so here's my collagen molecule. It turns out that these amino acid residues, these pi to pi star transitions, are actually organized in a particular way that they point in the same direction along the long axis. There's a non-vanishing component in which they all oscillate. Okay, and that's why this thing is active in second harmonic generation microscopy. This thing is called tropocollagen. This is one part of the triple helix structure of the protein. And if you stack them all together like that, then you form a so-called fiber. Okay, so this is actually a fibril. If you stack those fibrils like that, then you form a fiber. So it's a highly hierarchical structure. But the bottom line is, in all these kind of longitudinal structures, the molecular part that responds actually is kind of stacked in a certain way, such that the second harmonic generation signal does not disappear. Okay, so here is my, I have a couple of these fibrils next to one another, okay, and I'm all aligning them in the same way, okay? That means they all point with their heads in the same direction. I'm gonna drive them, and a second harmonic generation signal comes from them. Now I'm gonna do the same thing. I'm gonna take this whole stack, but I'm gonna rotate it by 180, okay? Like that. You see now there's a minus sign here. So their heads point now the other direction. So they flip by 180, and we have seen if you flip it by 180, the waveform shifts by pi, which means that you get a negative sign here. So there's a field coming out here, a field coming out there, but they have a different sign. They are out of phase, all right? If you square this one individually, you see a perfect signal. If you square this one individually, you see a perfect signal. But if you have a situation like that, where you have two pluses and two minuses next to one another, and I illuminate that area, then I have one wave of one phase, another wave of another phase, and they destructively interfere. So I expect when my focal spot hits a point where these fibrils point in opposite directions, that I don't see a second harmonic generation signal. Okay? That sounds weird, but in fact, if you look at this picture, where there is some color coding, the actual phase of the wave that comes out, you see that there's two kind of colors, green and red, and they are pi out of phase. That means that the green part points in one direction, and the red part points in another direction. And if you look at this part over here, right there, you see there's a dark line in between. That's because if your focus hits this spot, you get destructive interference. So the dark lines in your images are because of destructive interference, an indication that you have a situation where the fibrils point in opposite directions. Okay, now second harmonic generation is very popular. If you take a tissue sample like this, and there's many, many examples in the literature, this is an H&E stain, but if you do, for instance, fluorescence and second harmonic at the same time, you can see beautifully where the collagen sits here in green. You don't have to label anything. It's very high fidelity imaging. And in this case, people have studied the effects of fibrosis. And in fact, fibrosis detection is an important application of second harmonic generation. Another example is in vivo imaging. So here we combine the two effects. We have two photon excited fluorescence. You see the basal cell layer. This is all NADH fluorescence. If you go deeper into the tissue, you see blue. That's the second harmonic generation of collagen. This is the papillar collagen right underneath the basal cell layer. So this is in the dermis. And then you see some elastin fluorescence here in green coming up as well. So you see three components: collagen, elastin fluorescence, and NADH fluorescence, indicating where the cells are. So all label-free in vivo. So this is a beautiful illustration of the power of these approaches. Okay, I'm going to dive into the last part. Okay, it won't be much longer, folks, so we're almost there. And I'm going to talk about vibrational motions. Okay, so let's see what that's all about. So here's a molecule. This is actually a lipid molecule, or fatty acid. Okay, and I would like to, if you look carefully, you see things are moving there. You see that? It's like some breathing going on there. Those are oscillations of the hydrogen versus the carbon. So carbon-hydrogen oscillations. If I want to drive or excite those vibrations, I have to use energies that are much, much lower. Okay. In fact, I need to be in the infrared. So this is the ground state. This is my vibrationally excited state. And this up here, very high, is where the electronic transitions are. Okay. So I use much smaller arrows, much lower energies to drive those particular transitions. Infrared excitation is not always convenient in microscopy, and that's why people like to use the following. You go up with one photon, and then you wait for the photon to fall back to your vibrational state. This is an indirect transition, and that's the so-called Raman transition, named after this person, C.V. Raman, who discovered this effect in the 1920s. So here's an example of a vibrational spectrum. This is the absorption spectrum, the IR absorption. You see here is an axis in wave numbers. I'll tell you what that means. And you see all these features, all these lines, all these bands correspond to the vibration of particular chemical moieties. Okay, particular chemical groups have particular oscillation frequencies. So that is the amide 1. That is basically a protein. This is methyl stretches, which means a lot of organics, predominantly actually lipids, it turns out. And this is the Raman intensity. So we have IR absorption, Raman intensity. For Raman, you see the same kind of lines show up, although their relative ratios are kind of different, as you may notice. All right. So this axis here, kind of important. Wave numbers, what is it? It is a measure of energy. So if I write energy as the energy of the photon here, hc over lambda, okay, that's the photonic energy. And if I divide this whole thing by hc, so basically energy divided by hc, h is the constant of Planck, c is the speed of light, then I get this, 1 over lambda. And if I express lambda in centimeters, I basically get this unit. So what is nice about this unit is that it is directly proportional to energy, all right? And that it is a nice quantity. This is an easy to understand quantity. So you have a lot of kind of definition on this numerical scale. Okay, so here's a Raman microscope. You can purchase them if you have a lot of money. And it's actually kind of nice. Because what do you see? You see the following. So here's a cell, okay, in terms of Raman intensity. But what is much more interesting is to look at that cell in terms of Raman lines. Okay, so here is several spectra. You see here some pixels. You measure this Raman spectrum in red, and that spectrum looks like the spectrum of lipids. So that means that these red pixels here indicate the presence of lipids. If you look at this green here, which is more like a carbohydrate or starch, it means in this cell, in the green, is where the cell stores a lot of starch. And then the blue pixels here are proportional to this component right there, and they sit predominantly around the lipids right there in this part of the cell. So basically, Raman imaging allows you to create maps of cells based on chemical contrast, okay? And you don't have to label anything, you just make use of the intrinsic information that the molecules provide to you in terms of their vibrational spectroscopic features. Another example, on top here, you see cells, they are labeled with fluorescence, and at the top, the same cells are measured with Raman. So the red label is actin, you have here a lipid stain, this is a DAPI type stain, so the overlay gives you very nice contrast, but you can get the same kind of contrast if you tune into particular Raman lines, and the nice thing is that that contrast is now completely label free. I don't need labels, I can see these features because the cell tells me about its intrinsic vibrational features. All right, now Raman microscopy is powerful, folks, but there is one big downside because you probably you haven't seen a lot of Raman microscopes around, I assume, and that is because Raman microscopy is extraordinarily slow. Okay, it is so slow, in fact, that it becomes completely impractical for a lot of biological studies. What is the reason for that? Well, the main reason for that is that you see this little wiggle right there, that is so-called spontaneous emission. After this kind of like one photon comes in, you get this spontaneous emission coming out. This spontaneous emission is extremely improbable, okay? Extremely improbable, that's one. And the other part is that if you have an ensemble of molecules, let's say these people represent molecules, okay? Then these people, when you kind of give them a stimulus, they all start walking into a different direction, okay? In other words, the molecules, they all start to do oscillations that are completely unrelated to the oscillations of their neighbors, okay? But if you have, in this case, 4 molecules and you drive them in a Raman way, the light that comes out from each molecule has nothing to do with the light that comes out from the other guys in terms of their phase. So this is so-called incoherent light that comes off. Raman produces incoherent radiation. It shines in all directions. There's no coherence in this process. So there's an alternative, and that is so-called coherent Raman. It's a little bit more complicated, but the basic feature is the following. I again have one photon coming in, and this photon brings it back to this level, but now this photon is also delivered by me, okay? I'm putting 2 photons in, one up, one down, and the net result is I'm actively driving those molecules, but the important thing is I'm all driving them in the same way, in the same fashion, okay? And that means that you get something like this. All these molecules, they respond in the same way. They are phase synchronized. And that means if they start emitting, they emit in phase, and it turns out they are in phase in the so-called forward direction. So the beam here is coherently amplified in the forward direction, okay? The radiation is, again, Raman radiation. It's now coherent, and it adds up in one direction very efficiently, and this coherent amplification gives my signal an enormous boost. So much so that I can now detect almost 10 to the 5 times as fast. So what becomes completely impractical in spontaneous Raman becomes practical in coherent Raman. Okay, so the key feature is up and down, okay? It's now actively driven, and the photon that comes out, this guy, of one molecule and its neighbor are phase synchronized, and therefore it's coherent. This whole effect is a third order effect, and therefore it corresponds to chi3. Okay, so this is a third order nonlinear effect. The key thing that you gain from this is that this pumping through these probational states is much more efficient if you actively drive it than if you drive it through a spontaneous process, and therefore you cycle through this molecule much faster than you do in spontaneous Raman, and therefore you can generate many more photons. So the outcome is I can now scan much faster, and that is what it's all about. So here's this is my last image, folks. This is of an entire brain slice from a mouse. This mouse has a giant tumor in his brain. That's the blue part, okay? And then around it is the green color is actually the protein signature, the Raman protein signature. Actually, I should say the other way around. The green part is the lipid signature. The blue part is the protein signature. This is very rich in protein, this tumor, and that's how you can differentiate it from the rest of the brain tissue. So this is pretty big. It's about half a centimeter wide. The resolution is extremely high. It's about 300 nanometer lateral resolution, and there is chemical information in this image. Okay, so it's completely impossible to do with traditional methods with spontaneous Raman, but it becomes possible with this coherent Raman effect. You speed it up tremendously, and that opens up a whole new range of applications where label-free imaging is a possible solution to your problem.
Eric, how long did it take to acquire that image?
So this is a great question, Vasant. I think, you see, let's say this is one little frame. You can see the little demarcation if you look carefully, right? So each frame takes 1 second, and then you have to add up. You have to add up. So I think in all, this whole image probably took about 30 minutes.
Wow, pretty impressive.
Yeah,
there's another question. Yes.
Yeah, so how much faster is coherent Raman with respect to spontaneous Raman?
About I would say 100,000 times.
Okay.
Yeah. But you also have to pay more money to get an instrument like this.
But not 100,000 times.
There are trade-offs. There are trade-offs. So, okay. So, in conclusion, it's time to wrap up. There are some outstanding challenges because I've talked about optical imaging, nonlinear optical imaging as a great way to learn more about your tissue. We get some molecular information. There are ways to get a little deeper into the tissue. We use 3-photon excitation, right? Those are all examples that we went through. But it doesn't mean that we have succeeded really at what we want to do, because all of the things that I talked about require you to make a nice focus somewhere deep in the tissue. And that becomes increasingly more difficult if you go deeper into the tissue because of light scattering. If the light scatters on the way in, you don't have the opportunity to make a nice confined focus, which is what you need to generate these signals. So light scattering in tissues is one of the major limitations, okay? It limits the quality of the signal, the intensity, the resolution, and ultimately it just stops, put a hard stop to how far you can push this, right? So if there is a way to kind of mitigate or avoid this effect of scattering in tissues, you can just go much more deeper than we currently can. So the limit that we have seen in brain is about 1 millimeter, okay? And that is great, but that's still 1 millimeter. So for human diagnostics, that is not interesting whatsoever, okay? Maybe in a mouse, but it certainly has no application for human diagnostics. So circumventing this or doing something about it is a grand challenge. Many people are working on this. So first of all, can we understand this better, the scattering properties of tissues? And can we reduce them some way, somehow, so that we can go deeper and produce beautiful images at deeper depths? So if you are kind of motivated by this, then please start thinking about these problems and become part of a larger community who's thinking about these things. All right, that's enough. Thank you.
So Terrific lecture, Eric. You covered a lot of ground from fundamentals of nonlinear interactions of light with molecules, with a focus on biomolecules, and then going through kind of 3 vignettes of multiphoton, specifically 3-photon. And then you went through second harmonic generation and then finally vibrational imaging. So a lot of ground covered. Questions across those themes? Yes.
When you were beginning, I didn't really understand how a photon can be compressed. Were you talking about?
Yeah, okay, so it's a great question, and I'm not sure if this is the right platform to go too deep into it, but I can tell you the following. A photon traveling through space, you can compress it in the following way. You can simply have a little aperture and you send it through, okay? If it comes out on the other side, its size is about that size, okay? So the photons that make it through have that size. But that's only up to a certain point, okay? So, in fact, it's up to the diffraction limit, because beyond that, you really don't get light through anymore. But there is a way to do it, and this is, I mentioned plasmonics, okay? What is that? Well, basically, it's a small particle. You excite it or you drive it, and this particle is very small. It's much smaller than the wavelength of light, okay? And so what happens is this polarization that you create, this oscillation in this particle, is therefore happening on a scale much smaller than the wavelength. And the electric field associated with this oscillation can actually excite things underneath it, or it's in its immediate vicinity. And that means that if you have something in the vicinity of these oscillating electrons on these small particles, then the electric field associated with that oscillation is also confined and therefore can excite molecules close by in a different way than a freely propagating photon can. Okay? So the key feature is you need some sort of a particle, of a confiner, that takes the light in and translates this light into a so-called photonic polarization that you can use to excite or drive the molecules that are very close to this particle confiner. Does that make sense?
A little bit.
It is the basic principle of plasmonics. Okay, so if you have heard about surface enhanced Raman scattering or something like that, this is one of the basic operating principles, and it also pertains to some other areas that, again, we don't have to get into, but it is a known concept, and it is.
So Eric, just to express it in different terms, right? So you said that there's an intrinsic limit to the spatial confinement of light, which basically is an oscillation in electric field. Yeah. But if you're inducing an electronic oscillation in a particle in the presence of light, you're actually confining that electric field oscillation to the size of the particle itself, which
absolutely that is the whole notion. That's the whole
notion, right? So basically, the particle acts as a proxy for confining that electric field oscillation to a much smaller spatial scale than what's available through diffraction.
Yes. A freely propagating photon is basically propagating through vacuum, and in vacuum that has a certain size, which is basically approximately the size of a wavelength, which translates approximately into the diffraction limit. But yeah, if you have a small particle, you polarize that particle, then the electron oscillation associated with it is an electric field. That happens on a much smaller scale. So yeah, confining by particles, small particles like gold nanoparticles or what have you, is a very important trick in spectroscopy.
Great question. Other questions? Yes.
In coherent Raman, does it also reduce autofluorescence from the tissue, or is it still the same?
Oh yeah, it's a great question. So if I do a coherent Raman experiment, do I see maybe a background signal from autofluorescence? Is that the question?
Yeah.
Yeah, okay. So yeah, if you send in these pulses of light into your sample, then you may excite fluorophores and they may radiate through a 2-photon excited fluorescence mechanism. And those photons will be around. So your challenge is to put filters in front of your detector that isolate the coherent Raman signal and reject that signal from the fluorophores. Now, what happens typically is that some people say, wait a minute, that signal is already there. So what I'm going to do is I'm going to add another detector with a different filter in front so I can detect both. Okay, so I have my coherent Raman signal at one particular wavelength, and then I detect also the emission band of my fluorophores, and therefore I can see both. So That, of course, is called multimodal imaging, and it's very popular. It makes more efficient use of the signals that are coming off your sample.
Thank you.
Yes.
Back to the fibril collagen example when they're facing two opposite directions. You mentioned that the second harmonic signal is deconstructing because they're facing opposite directions. So if it's a deconstructed signal, are you saying we can still visualize that?
No. Basically, think about these two oddly shaped molecules that I drew, like it's two pear-shaped molecules in opposite directions. They produce two waves. They both radiate. They both produce a second harmonic signal because in that area, when you detect it, they have opposite phases. They destructively interfere, and nothing comes out. So when you have opposite-oriented structures, or randomly oriented, in fact, which is the same way, because if you're random orientation, then there's always pairs of opposite molecules in opposite directions. So if it's randomly oriented or perfectly opposed to one another, your second harmonic signal at that location is simply not there. Okay, so that's why you see those dark lines. That means the absence of second harmonic generation. You don't detect it, even though on the molecular scale they oscillate with the second harmonic frequency. There's no light coming out.
Right, so that black line is basically the interface between collagen on one side oriented in one direction and then collagen on the other side oriented in the opposite direction.
So what's the green and red stripes in that image?
It's also collagen, but they're oriented in opposite directions.
Okay.
Yeah, so the colors, the colors are false colors, right? This measurement, that I showed is kind of done in a particular way that allows you to see what is the phase of the second harmonic signal. And you can, if you do that, then you get two different phases, one in one direction and one in the other direction, which means high out of phase, okay? And the color coding just shows that. So it's a false color coding. Green means in one direction, red means in another direction, and that tells you that, yes, wherever they meet in opposite directions, you see a black line, because in those locations, there's destructive interference. But as soon as your focal spot is fully in the green part, you only see perfectly strong second harmonic generation. You only see the destructive part if your focus hits the interface between the two, and that's why you see there a black line.
Okay, thank you.
How do you align those collagen cells?
Fortunately, they do it by themselves. That is just the structure of collagen. So collagen is a highly aligned extracellular structure, and we take advantage of that.
There's another question. Yes.
I guess my question is, are there similar limitations to the third harmonic generation, or is there like a benefit to where maybe now you can start to see things that are not as organized?
Yeah, so the third,
sorry.
Yeah, that is a good question. And I think what you want to hear is maybe the difference between second harmonic and third harmonic. Like, you know, do they see the same things, or do you see something different? It turns out, even though they both have the word harmonic in it, they see completely different things. Okay, so the first notion is that the second harmonic generation is proportional to chi2, and this chi2 is extremely sensitive to the orientation of the molecules, as we have seen. But it turns out the third order response, chi3, which is what third order harmonic generation is not sensitive to the orientation of the molecules. Okay. And therefore, you can always see some third harmonic generation signal in principle. Now, if you do third harmonic generation microscopy, then you notice that if you just put, a sample that's just water, you don't see anything. Okay, and you're like, how is that possible? I have water molecules everywhere. Third harmonic generation is not sensitive to orientation, so I should be seeing something. But it turns out the signal is depleted because of a completely different mechanism, and that mechanism has to do with it has to do with the so-called GUI phase shift in focus. And it is a complication that basically avoids the ability to generate signal. If you excite the entire focal volume, the molecules actually, turns out, are out of phase because of the so-called GUI phase shift. I don't think I should be going into too much detail about it. But the interesting thing is, the bottom line is that if you focus into a bucket of water, you don't see anything. But if you focus onto a very tiny particle that is very small, it's smaller than the focus itself, you actually see some signal. Okay, because you break this condition of the GUI phase shift destructive interference, and you still see some signal. So third harmonic generation actually is a very good technique to see small particles, and those particles must have a slightly different nonlinear susceptibility than their surroundings. If they do have that, then they show up in THG microscopy, third harmonic generation microscopy, and therefore, if you look at the literature, what people use it for, they typically detect edges or small particles based on this optical technique. So the bottom line is it's very different from second harmonic generation. You see completely different things. And the bottom line is that the reason for that is that they have very different symmetry properties. Okay? So the Chi2 depends on molecular orientation very much, as the third harmonic generation, the Chi3, does not.
Our questions. Yes, let's go to Shilpi now.
Yeah, I just had a question about the coherent Raman, like specifically how we're changing the pulsing of the light to make it active and a lot have it happen at a high probability. Like, what exactly are we changing?
Okay. So what we're changing in coherent Raman is indeed we change things on the excitation side. Okay, so in regular Raman, what you do, you have a CW, continuous wave laser. You send that laser into your sample, and then you see some light coming out of different colors. That is the Raman scattered signal, spontaneously Raman scattered signal. We want to get rid of this spontaneous effect, and therefore we want to not just have spontaneous coupling of the light to the vibration, but we want to actively drive that vibration. And the way we do that is by sending in two colors at the same time. So two lasers, two light beams at the same time. And we drive that molecular vibration actively. And one way you can think about it is, again, if you think about striking two piano keys at the same time of slightly different tones, sometimes you hear an overtone that is the combination frequency or the difference frequency between the two. Okay? The difference frequency tone is basically the tone with which to drive the molecule. So that's the energy of one photon minus the energy of another photon. That is the difference frequency. So you drive the molecules actively through the difference frequency of these two incoming pulses. So that's one thing, you need the two colors. The second thing is that in order to make this nonlinearity efficient, you need to have high intensity, and the best way to do that is by delivering the light in pulses. Because during the pulse, the intensity is super high, so very high nonlinearity. And then in between, you have nothing, okay? And then you wait for the second pulse, so you benefit again from your high nonlinearity. So in regular Raman, we use CW light, continuous wave, and in Raman, we use pulse light to amplify the nonlinear effects over the linear effects.
And then do the wavelengths of light you choose depend on the tissue you're imaging, like the vibrational quality?
So the wavelength of light is we have to carefully select. The main thing for coherent Raman is that the two colors we put in, the frequency omega-1, frequency omega-2, the difference between them, omega-1 minus omega-2, must be the frequency of the molecular oscillation, right? So that means we cannot just send in any arbitrary two colors. Those two colors are linked to one another through the vibrational frequency of the molecule that we'd like to see. Now, other than that, you're free to choose. As long as the frequency difference is fixed to drive your molecule, you can put that frequency anywhere in the spectrum, your excitation spectrum, and you select typically a color that is favorable in terms of light scattering. So we move the excitation wavelength further towards the red. So typical colors used in coherent Raman are colors between 800 nanometers and 1000 nanometers.
Thank you.
Yeah, so this is more like a divagation than anything else, because I'm coming back to the last slide where you introduced this challenge related to scattering.
Yeah.
So lately I've seen a couple of papers, more than one, talking about, let's say, tissue optical clearance, right?
Yeah.
Looks like tissue looks transparent or more clear than in natural conditions or situations by using chemical compounds, I think mostly tartar or something like that. And I don't know if it would be possible to combine these with nonlinear optics microscopy, or if someone already did that, saw some results.
Yeah, excellent question. Optical clearing is extremely popular. People use it for all kinds of things, including coherent Raman, second harmonic generation, cytofluorescence. Yeah, this is something people have done quite successfully because it really addresses an important limitation. You reduce the scattering, you can go deeper, right? It is not something you can apply all the time because it's really hard to do it in living specimens, especially in humans, right?
Yeah.
But certainly ex vivo, it is a great way to do it. In some animal models, you can also apply it within certain limits. So it is one way to go around this problem of tissue scattering. So yeah, absolutely.
Okay, and how much deeper can you go with optical clearance?
Well, you can go quite a bit deeper. I think sometimes up to a factor of 2. And then at that point, you also hit another limitation, which is the so-called working distance of your objective lens. So the working distance typically is, a couple of millimeters. And so beyond that, it's difficult to get in. So there are objectives, microscope objectives that have much longer working distances. And with those, I expect you can maybe push it a little bit more. But I think a rule of thumb about a factor of 2 is something you can achieve.
Thank you.
One of the key factors with clearing is you don't want to perturb what you're trying to measure, right? So you might gain the benefit of being a little deeper, but if you're delipidizing and you want to look at lipids, that's obviously a bad trade-off.
Yes, that's right. Yeah.
Okay, I think this is a great start. Thank you, Art, for a terrific lecture. Great, obviously great interaction.
Thank you, guys.